Hello, welcome to Chapter 2. In this chapter, we talk about gates, circuit, and flip-flops. I will not read everything. I will just explain certain things, and you need to read it carefully. On this slide is combinational logic and sequential logic. Combinational logic depends on the current input. It does not remember the previous result, while a sequential circuit remembers the previous result, as well as using the current input. Therefore, a sequential circuit is a memory element. You can read the whole slide. Here, logic values, you can read it on your own. And gates, you can read it on your own. Fundamental gates, and, or, nor, exclusive or, etc. Okay, we will talk about them. The AND gate. Let me talk about the AND gate. The AND gate is what we discussed in Boolean expressions. When you have a Boolean expression, A and B, it's equivalent to multiplication. For example, if for these two inputs, if you look at this table, okay, these are called the truth table, if you remember. If you have 1, 0, then your output is 0. Okay, if you have 3 inputs, if you have 1, 0, then the output will be 0. It's exactly the same as multiplication. So that's why we use this symbol for the AND gate. That's the multiplication symbol. And this is how it is expressed okay, here is the true symbol. That's the operator. So this is how it's expressed. That's the AND gate. Now let's go to the OR gate. The OR gate is just like addition. And these are the truth tables, and this is the symbol. So for the OR gate, you only need 1 true value. Then your result is not 0. Okay, so just like addition, if you have 1 number that's not 0, then your sum is not 0. So only when all of them are zeros, then your result is 0. That's all. So for AND, you need 1, 0 to make the output 0. For OR, you need 1, 1 true to make the result true. This is the comparison of AND and OR, and you can read that on your own. Number 8, the NOT gate. This is the slide 8, the NOT gate. It's also called an inverter, and this is how it's expressed. A triangle and a little circle there to negate it. So if the input is 1, the output is 0. If it's 0, the output is 1. That's the truth table. Very, very simple. Now, because this inverter symbol is a little bit more complex, so we simplify it using this bubble. It's called a bubble, a little circle. That means the value is inverted. So if A and B are both 1s, suppose the input for A and B are both 1s, then 1 comes here, inverted becomes 0. Then if you have 1, 0 with this AND gate, the result is a 0. So this input is a 0. Now here, this is a 1. It comes here, inverted, it becomes a 0. And so now you have a 0 also. 2 zeros come into this OR gate, you have a 0. So 1, 1 is inverted to a 0. Okay, that's the that is a gate. It's just telling you, I'm just showing you how this inversion works. Let's go to number 9. Examples of a digital circuit. Okay, so this is called the sum. Remember, OR is the sum of AND of products. These are all AND gates. So they are all product, called product circuit. So one input can have two values. We said that, one bit can have two values, either 1 or 0. So if this is a 1, it comes here, it's a 1. But if it goes this way, it becomes a 0 because of the inversion. Okay, so these are all product circuit. And then if you have one that is true, you will have a true because this is the OR product, or OR gate. Okay, this one is called the product of sum circuit because these are all OR gates and they are sum gates. And this one is an AND gate. So this is a more stringent requirement because you need all of them to be true in order for this to yield a true. And once again, you have one bit that will give you either 0 or 1. Okay, so it has two pathways. This one will be negated, and this one will keep the original value. Now, let's go to slide number 10. Number 10 is derived gates, NOR, NAND, exclusive OR. A NOR gate, okay, these are the truth tables again. A NOR gate means you have an OR result and then it's negated. So if you have 1 and 1 as A and B coming in, an OR gate would give you a 1, but it's negated, so it becomes 0. Okay, for this one, this is the NAND gate. If you have 1, 1 coming in, it should give you a 1, but it's negated. It becomes 0. Exclusive OR, this is a new gate. Exclusive OR means it's looking for the difference. Only when the two inputs are different, then it will give you a true state. Okay, so if A is 1, B is 0, then you will have a 1. If A is 1, B is 1, you will have a 0. That's what this truth table is telling you. So if you look at this, exclusive OR, this is the symbol, okay, the plus sign with a little circle around it. And so when they are the same, when the two inputs are the same, you have a 0, false state. When the two inputs are different here, 0, 1 and 1, 0, then you have a true result. When they are the same, you have a 0. So that's the exclusive OR gate. And this is how it's expressed in a symbol. Okay, this is exclusive OR. This is just the gate that will show you how exclusive OR works. Let's trace this once. Okay, so suppose A and B are both 1s. Those are two true inputs. The result should be a 0 because they are the same. Okay, let's see if it works that way. 1 coming in is a 1. 1 negated becomes a 0. So this AND gate gives you a 0. Let's look at this one. 1 coming in as a 1, but this one coming in, this A coming in, negated becomes a 0. So this AND gate gives you a 0 also. Thus, the result is a 0. Let's look at 1 and 0. So A is 1, B is 0. 1 coming in, 0 negated becomes a 1. So this AND gate gives you a 1. Okay. A is 1 coming into this. I'm sorry, did I say? Yes, okay. Okay. A is 1 coming in, this becomes a 0, right? Okay, so as soon as you have a 0, then this AND gate gives you a 0. But remember, this AND gate gave you a 1. So this is an OR gate, it gives you a 1. So when it's 1 and 0, it gives you a 1. That proves that this gate works correctly for exclusive OR logic. This is a circuit, not a gate. Okay. So this is the exclusive OR. By the way, this is how you express it in words. XOR is also called XOR or EOR. Okay. So please read the slide. Let's go to slide 12. NAND gate. This is a side note, actually. I just want you to know. But NAND gate can be used to construct a NOT or AND gate. And therefore, NAND gate is called the universal gate. Let's trace them. Okay, if A is 1, negated, it should give you a 0. Okay, now let's see. This is a NAND gate, right? A NAND gate. Okay, so 1 coming in, split, so both signals, both inputs are 1. 1 coming in, that gives you a 1, but negated, that gives you a 0. So this is using a NAND gate to construct an inverter. Here, AND, 1 and 1 should give you a 1. Let's see. 1, 1, coming in, this AND gate gives you a 1. Negated gives you a 0. Coming in, 0, split into 2. 2 zeros coming out of this AND gate gives you a 1. Now a 0 negated gives you a 1. So this 2 NAND gates together construct an AND gate. And then this is the NAND gate constructing an OR. Okay, so if we have 1 and 0, let's see. 1 coming in, this AND gate, 2 1s becomes 1 negated, it becomes 0. And this is 0, it becomes 1. But this is AND gate, well, as soon as you have 1 0, it will give you a 0. But negated, it will give you a 1. So 1 0 coming in gives you a 1. That proves that NAND gate is called a universal gate because it can be used to construct NOT or AND. And from those fundamental gates, you can construct all kinds of circuits. This is an example of a digital circuit. A circuit with 4 gates. Once again, you read those explanations. I will just explain this diagram, this figure. Okay, so here we have 2 inputs, A and B, coming in, and we also have an external signal called X. So this explanation is saying X is a signal coming from the instruction. When X is 0, it is a logical AND. When X is 1, it is a logical OR. So let's see. If A and B are both 1s, okay, and X is a 0, then our result should be a 1 because when X is a 0, it is a logical AND. When X is 1, it's a logical OR. So 1 and 1 coming into this OR gate, it becomes 1. 1 coming into this AND gate, and this X is 0 coming into this AND gate, that makes this R intermediate value a 0, 1 and 0. However, let's look at this one. 1 coming in is 1, 1 coming in is 1, that gives you a 1. Coming here, this is an OR gate, so you do have a 1. Okay, that proves that when X is 0, it is a logical AND. Let's see, when X is 1, it is a logical OR. So, let's see, suppose A and B, A is 1, B is 0. And logical OR, it should give you a 1. So 1 coming in, and this is 0, it doesn't matter. P, the intermediate value, is 1. So you have 1 coming to gate 3. And this is 1 coming here, and this is 0 coming here. And that gives you a 0 because it's AND. Okay, so this P, just now we said it gives you a 1. You have a 1 coming in, and then X is 1 also. So 1 and 1 are, oh, did I say that already? R gives you a 1. So this is an OR gate. C is 1. So when X is 1, it functions as a logical OR. Okay, that is what this circuit is about. Let's do 2 more slides and then we take a break. This is the half adder and full adder. Okay, so when you add 2 bits, you are basically looking at the difference, which is really exclusive OR. That's why you see this symbol. That's for sum. Okay, both are the same, the result is 0. No, here, the sum is 0. Different, that's 1. Different, 1. They are the same, your result is 0. This is sum. You remember when you do addition, you also have a carry, right? So when they are both 1s, your sum is 0, but your carry is 1. However, with this half adder, you only have 1 bit. So here the result is whatever the difference is, and the carry bit is not remembered. That's why we call it the half adder, okay? Because it ignores the carry bit. And also remember the half adder uses XOR logic. That means when you add 2 things together, 2 bits together, you are looking at the difference. Let's go to this full adder circuit. Full adder means you have 2 half adders. This is 1 half adder, I tell you here, and this is another half adder, the second half adder. So the addition to this is that you have a carry in. That means, okay, let's do a sum of 2 bits. Now we have a carry out. What do? We input that, let it go back to be the carry in. So let's look at this addition. After this, we will be done for this video. Okay, so 1, 1, 1 plus 0, 1, 0. 1 plus 0. Okay, so A is 1, B is 0. 1 coming in, 0 coming in, exclusive OR, the sum is what? 1, because they are different. So you have a 1 coming here. Okay. And then 1 and 0 coming here to gate 2. A is 1, B is 0, that carry gives you a 0. So this is a 0 here. And this is, this sum, gate 1 gives you 1. 1 coming in, and carry in, we have nothing. So this gives you a 1 because it's exclusive OR. So your sum is 1. And this carry in is a 0. As soon as you have a 0, the AND gate is a 0. So you have carry 2 is 0, carry 1 we just calculated is a 0. So your carry out is 0, and your sum is 1. Now let's go to the second 2 bits, 1 and 1. Okay, A is 1, B is 1, coming in, sum 1 is 0, which is correct, right? Sum 1 is 0. And carry in is 0, and so 0, carry in, and sum 1 0, your sum is 0 because this is exclusive OR. Okay, 1, A1 comes to gate 2, B is 1 coming to gate 2, carry 1 gives you a 1, and 1 comes here. We do not even need to do this part because this is an OR gate. our carry 1 is a 1. So just to satisfy our curiosity, let's do this one, see what it is. But it doesn't matter really. Carry in is a 0. So as soon as you have a 0 in an AND gate, it's a 0. Okay, but this carry 1 is 1, so we have a 1 coming out. And if you look at this 1 plus 1, that gives you the sum of 0 and the carry of 1. So now that carry 1 will come here as a carry in. Okay, so now the third set is 1 plus 0. A is 1, coming here. B is 0, exclusive OR, sum 1 is 1. And the carry in is 1. Exclusive OR, your sum is 0, which is correct. If you do the addition, your sum is 0. Now let's look at this one. We are looking for 1 carry. So this carry in is a 1 coming here. That's a 1. And this A is 1. This B is 0. Exclusive OR gives you a 1. So this AND gate really gives you a 1. Now that 1 comes to this OR gate. We do not care what this gate is. Now we have a 1. Our carry out is a 1. So for these 2 bits, 1 and 0, you have a sum of 1, sum of 0. We did that. Sum of 0 and the carry of 1, which proves this full adder is correct.